not sure why there is
the mango is in there.
It's a mango or a coconut? Oh, it's a mango.
Yeah.
All right, let's get started. Welcome back to the afternoon session. And the first talk in this session is by Dhiraj, and he's going to be telling us about CMB across scales.
Thank you, Susmita. First of all, let me thank the organizers for inviting me and giving me the opportunity to speak here. I have been asked to talk about CMB Bharat, specifically ECHO from the CMB Bharat. ECHO is a ambitious mission proposal led by Professor Tarun Sauradip, exploring cosmic history and origin, and CMB Bharat is our consortium collaboration. Before going to that, to put it in the context and put it in the context of this meeting, I'm going to talk about CMB across scales, what we learned from different CMB missions, starting from WMAP and what we are there in stores. And I will talk about consistency between observations because that is very important, because whenever there are anomalies or tensions, we talk about new physics, and that is where I would like to show you that consistency check is very important because sometimes systematics, or most of the time systematics comes in the way of understanding the physics, and in most of the times the standard model is good enough, but we are missing somewhere in understanding the experiments. And we basically run for new models, and at least that has been there for the last couple of decades. So after that, I'm going to talk about what is the need for space-based mission. So this is the brief plan of my talk, just taken from the 2 lines of my title. So after the consistency checks, I'm going to talk about what is the need for the space-based mission. I think everybody knows that we need space-based CMB mission, covering from largest to the smallest possible scales that we can achieve from the space. And then I will come to ECHO from CMB Bharat. Okay, so to start with, let me talk a little bit about cosmology, the way we understand it. So there are some assumptions, some principles, guiding principles on which the understanding of the cosmology is based on, and then mostly it is observations right now. So the homogeneity and isotropy assumptions regarding the universe, assumptions supported by the observations, helped us to use the Einstein's equation in describing the universe. We could write the Einstein equation, which is a local equation, and we can explain the universe using the g mu nu equal to 8 pi g t mu nu, which gives us the Friedman universe. However, in the recent decades, the new physics has mostly been prompted by observational evidence rather than a drive for theoretical completeness. We can talk about dark energy, dark matter, or inflation as well. But again, I would like to say that this is not the complete story. Even before the observations, many legends proposed inflation and few other things that were supported by observations later. But mostly, that is why I added this term mostly, that our hunt for the new physics nowadays is mostly been prompted by observational evidence rather than a drive for theoretical completeness. Since WMAP, we have been able to rule out several models of cosmology, for example, lambda phi 4 or m square phi square with Planck, and many other models based on the constraints on scalar spectrum, principally on the scalar spectral index, and the non-detection of the tensor modes. However, we have not been able to find any strong signatures of new physics, strong means of the order of even 3 sigma, beyond the standard model, which I basically call this as standard model, lambda CDM model plus the primordial power law spectrum, which we use as 6-parameter model in our analysis. Although the anomalies and tensions actually can be like 3 or 4 or 5 sigma, the theories that tries to explain them, we do not get evidence more than, not evidence, but or support more than 2 to 3 sigma. With WMAP, Planck, BICEP, ACT, I should put also the SPT, we have noticed this multiple times. And for example, let us take some cases. This is a non-exhaustive list, by the way. So I have missed many things, but few of the things that I have chosen along the way to highlight. WMAP hinted for non-Gaussianity, large non-Gaussianity. It was a hint at 1 sigma or nearly 1.5 sigma, but we had to wait for a full sky Planck survey covering from the large scale to largest to the smallest possible scales by Planck to be disappointed. Sometimes we find we are hit by systematics. Planck picked up 4K Kula systematics near L equal to 1800. And if you were trying to do some power spectrum reconstruction, this is our work in 2014, we found this kind of change or this kind of wave in the primordial power spectrum, which seems to be nearly 3 sigma significant, but it was indeed a L equal to 1800 systematics because of the 4K Kula line. Bicep 2 detection of B modes, it was indeed a B mode, but we had to wait for full sky high frequency map from Planck to debunk that it was not primordial, but it was coming from the dust. Recently, Planck data found the indication of excess smearing of peaks. This is what is dubbed as A-lens anomaly or lensing anomaly, was highlighted in Planck collaboration in 2018 paper. The same anomaly is related, the same effect that we are seeing, the smearing of peaks, the exactly same effect is related to the closed universe detection at 3 sigma. This was also highlighted in Planck 2018 paper. So either you use lensing, you say that my lensing is smeared, lensing is more, the peaks are more smeared than the GR prediction, or you say that it is closed universe, you get 3 sigma significance for both of them, for omega k either or A lens. In Planck PR4 N-pipe CAMSPEC analysis, we found that the significance is reduced, nearly 1.5 sigma from 3 sigma. However, a note I would like to mention, CAMSPEC uses aggressive sky, like 80% in temperature and polarization, does not use 100 gigahertz sky map. Definitely there are reasons for that, but again, this is just a note. But Planck PR3 PLIC analysis always showed that there is a problem, or there is some systematics or something like that, or some hint of new physics. ACT DR4 data and SPT data showed tension 3 sigma with Planck in the determination of spectral index. This SPT data I am talking about is precedes the ACT DR4 results. H0 tension, for example, was initiated was responsible to initiate many models. For example, I'm going to talk about the early dark energy, which is the most discussed model proposed by Vimyapula et al. In 2019. However, you should know that that significance was driven only from the prior on the Hubble parameter. If you try to fit early dark energy to Planck, you get that the peak is the posterior peaks at FED or fractional the early dark energy contribution at FED equal to 0. So you do not get any improvement in fit from Planck. What it does is that it allows the H0 to go high. It is not that it allows the H0 to go exactly high, but it allows the H0 error bar to inflate. And then when you are using the Hubble parameter constraint or Hubble prior, it is trying to go to the sweet spot and fit and pick the early dark energy. Later on, it was noted by 2 groups that ACT DR4 supports the model for higher spectral, supports the early dark energy model. If you take Planck up to 650, and after that if you take SET, then you get 3 sigma significance for early dark energy. But it was positive, but it was actually driven by this higher spectral tilt that ACT was demanding. And higher spectral tilt, as I was commenting in Celine's talk, is positively correlated with Hubble parameter. So, and that actually drives the thing. And I will show a Planck and SET comparison of power spectrum reconstruction and show you exactly where Planck and SET did mismatch in the cosmological scales. Presently, with Planck SET DR6, DESI DR2 BAO, we have hints for low neutrino mass. And now if you allow, for example, there are many groups who have written papers that if you allow negative neutrino mass, it is going towards the negative neutrino mass. But I would like to say that you should ignore negative neutrino mass priors. And to me, I think we should not allow the neutrino mass even in the prior level to go below 0 electron volt, or maybe even more theoretically go below 0.06 electron volt. But it indeed goes for a low neutrino mass. than earlier, although I would not call it a tension, but people are talking about new physics. So while hunting for new physics is exciting and very important, and I have done this exercise a lot of times, but it is also crucial to test for the consistency between observations of similar nature. So consistency tests across cosmological scale can reveal the extent of support for new models and also can hint towards systematics. And for example, I'm going to talk about this one. See, even if you do this addition interval exercise, if you cut the Planck multipoles up to L equal to 1000 and after L equal to 1000, then you will see that there is a 2.5 sigma discrepancy between the parameters. However, Planck 2018 consistency check settled the debate. This is the Planck 2018 checks. It is not exactly 1000 cut, but the cut was between 2 to 800 and beyond 800. So it showed that it is mostly consistent. All the inconsistencies are within 1 or 2 sigma. So this is important again to say whether we need new physics or not. We did a consistency test between WMAP and Planck back in 2014. What we try to do is that we try to do a simple test that we will reconstruct the primordial power spectrum from both WMAP and Planck. So we know that the power spectrum, the primordial power spectrum convolved with the transfer kernel gives you the angular power spectrum. We do the reconstruction from Planck, and then we smooth it with a Gaussian kernel, and then we fit it to the WMAP, allowing for amplitude variation. And these are the results. This is the low L part of the Planck. So from 2 to 49 around that time, this was the Planck first release, 2013. And we found that the reconstructed spectrum that fits the Planck data better than the standard model is also fitting the WMAP data better than the standard model. That means that it is not just the spectral tilt, or there is not just the consistency between spectral tilt and the amplitude. There is a consistency between the different the CLs at different multiples. For example, if there are features, to put it more in an easier way, that if there are features, if there are deviation from the standard model, you are going to see that you were seeing that in the WMAP as well. If you do it for the all the frequency channels of the Planck, combining them, you will see the same story. But at the same time, you see that it is not fitting the WMAP better unless you allow an amplitude shift. So this was another systematic that Planck revealed, that there is a 2.5% amplitude mismatch because of some calibration issues, okay, between Planck and WMAP. So ACT-DR4 and Planck, we did a recent analysis actually last year. So before the ACT-DR4 release, that ACT found out 3 sigma discrepancy between Planck PR3 and ACT-DR4. That exists also in the determination of the baryon density. If you add constraints from Planck on the spectral amplitude L equal to 220, it removes the tension, but it brings in worse fit compared to the standard model. And ad hoc rescaling of TE spectrum also removed the discrepancy. We tried to see where the discrepancy lies. So what we did is that we tried to get the primordial power spectrum from Planck and ACT by Richardson-Lucy or modified Richardson-Lucy reconstruction. It is done in this paper. This was the Planck standard model best fit. This was the ACT standard model best fit. As you can see that this goes for the red tilt, 0.96. This is probably 1.05 or something like that. So they do not talk to each other. And this is the reconstructed NS, which is d log PS d log Km plus 1. So Planck reconstruction is consistent with this. When we do for the ACT, we find that ACT data is also consistent with Planck at intermediate scales and at very small scale, both going for the red tilt, but here there is a deviation. So we found that there is a disagreement between the data between 0.08 and 0.15 megaparsec inverse, and that was actually driving the significance of many of the new model of cosmology. I will not go beyond that. So I'll quickly focus on the echo now. So I will try to argue why SCMB space mission is important and why we need it from larger scale to arc-minute scales. So even if you forget about any new physics, for example, even in the standard model, there are many unknowns. For example, primordial B modes that translate to tensors, reionization. These are all known physics, but we do not know them very well. Neutrino mass, we know that neutrino has mass, and dark matter properties. So if we have a space-based CMB mission, of course ground-based can also help, we can convincingly answer them because we have more frequency channels. I'm going to go to the advantages of the space-based CMB mission. So a cosmic variance limited space-based CMB polarization mission covering from the largest to small cosmological scales, it cannot go as small as ACT or SPT can go. So has several advantages over a ground-based surveys and can address all of these above questions. At the same time, it provides consistency checks between several frequencies, because when we go in space, we have the advantage of putting many frequency channels because of no atmospheric contamination. So why space-based missions? What are the advantages? These are something that you all know. So we have the access to the largest scales. We can reach to the cosmic variance limit, even if, yes?
I have a question before you go to CMB Bharat.
Yeah.
On the previous part, so ACT don't see the large scales, right? It's a partial sky experiment. So how do you, so ACT pole uses the information of larger scales from Planck.
Yeah.
So, but you need a prior on the tau or L modes in order to get a consistent power spectrum measure. Maybe Raman can add more on that. But what I'm a bit curious about is ACT pole don't see a AL greater than 1.
Yeah.
It sees a consistent result. So how do you patch these two? Like, do you get a consistent result in your P of K? Do you take into account the tau prior as per Planck, or what prior do you take?
Well, so you are talking about why we are not getting, so you are saying that whether tau and AL are related or not.
So I'm saying that ACT pole sees everything at the large L. So it scales with the L modes at the Planck.
You are talking about anisotropy or lensing deconstruction.
As well.
CLTE as well. Okay.
So now you need to, because ACT pole uses the low L information of Planck in order to get the constraints.
Yes.
And how do you get it? Because I am a bit confused about the not matching of ACT with Planck. So I want to understand.
Not matching of ACT with Planck. Okay, so let us, if we are just concentrating on the standard model, that is the 6-parameter model, not going to the AL, if you just look at this, you see that there is a discrepancy, and the way it was advertised that no, ACT actually wants a scalar spectral tilt greater than 1. That is not true. There is a discrepancy only here, so it might be probably a systematics. So that was my concern, and that was my my main agenda here. And regarding AL, so AL part is actually coming from around L equal to 850 or 750 or something like that to 1500. So around that part, still Planck is somewhere better than the ACT, because L equal to, because even in the latest ACT DR6 result, the Planck is cut off after L equal to 1000. So after 1000, ACT signal to noise ratio becomes better than Planck. So I am not, so there I have many other suggestions of new model. For example, it might not be a lensing, it might be something else that is supported by both the data sets. So yeah, we have certain other results, we have certain other models, but again, I'm trying to avoid all the new physics models. So that's yes. Lyman, you have?
No, I was going to say, if you've done ACT plus WMAP, I think those would have been ameliorated.
ACT plus WMAP.
Right.
I am not using Planck here as well.
No, but I think that's...
This one is Planck alone, and this one is ACT alone. This part, just to have completeness, I am just using Planck.
I think for the, I mean, Shubhagi pointed out, right, since there's no, if you add ACT plus WMAP,
Yeah.
it comes closer to Planck than you might naively think from this presentation.
Yes, but here, for example, when I'm doing the reconstruction, Planck is not playing a role in this part at all.
Yeah. So,
This is the reconstruction. Yeah.
No, I'm talking about all the other ones you pointed out. The index
Yeah.
is because there's no L support in ACT. Period.
Okay, so when we are, okay, so index, so we should actually focus on this one, because when you have a non-scale invariant curve, when you have running, spectral index does not tell you the whole story. This is just a representation. What you actually should compare here is this one, the power spectrum reconstruction, here and here.
Yeah, I'm saying that we can talk about separately. The purple line is, I think.
Oh, the purple line is basically coming, oh, you are saying that if you are actually using WMAP plus
ACT, you don't have, which is completely independent from Planck. I mean, in your
Yeah.
big picture, that's what you want to do, right?
Exactly, but here also, for example, if you are using either the constraint on the power, the CLTT power at L equal to 220, the first acoustic peak,
Sure.
from Planck, or either WMAP, then you would have seen that it is consistent. But again, it comes with a reduced improvement, a reduced fit. What I'm trying to argue is that whatever ACT is seeing, that is good enough to constrain NS, and that is why you are getting 3 sigma discrepant result from Planck. So your NS is 1.05 plus minus, and in the next release, you did not see that. What happens is that in the next release, we are not picking up this one. It is actually consistent with Planck now.
Yeah. No, I'm
So this was
yeah, go on.
So this was, so what I am trying to say that this was definitely a systematics because it is not there anymore, if we are saying that ACT DR6 is correct.
I can say, you mentioned the TE, that actually the low L TE
Yes.
was due to a beam systematic.
Here in the ACT paper, what you say that in order to get this, reduce, scale it, then.
That's a way to account for the beam systematic.
Okay. So, so we can reach to cosmic variance limit, and we have more frequency channels, good for consistency check, good for having more data, and stable observing conditions, and we need far less numbers of detectors compared to the ground-based surveys. From there, let me just come to Core M5 mission. Around this time, I was at APC, and Europe proposed Core, Cosmic Origins Explorer, and to ESA M5 proposal, call for proposal, with an ambitious 1.7 microkelvin arc minute sensitivity with 19 channels spanning from 60 to 600 gigahertz. It did not pass the ESA screening in 2017. So the reasons cited are costs, and the next reason is also related to the cost that it was proposed without firm commitment from an international partner. So Core M5 went ahead with Envision, Theseus, Spica into phase A. So then the story of ECHO comes in. Oh, I have, okay. So in February 3, around similar times, 2018, so ISRO announced this announcement of opportunity for future astronomy mission. ISRO, the Indian Space Research Organization, wanted to invest in basic sciences or basic cosmology, and they advertised this announcement of opportunity. And Tarun Sauradip, at that time, he was at IUCAA, he initiated an effort to prepare an India-led mission proposal with Core M5 upgrade and with the possibility of a spectrometer with a few Core M5 members as point of contacts, and as a joint ISRO and ESA mission. About 100 Indian cosmologists working within and outside India created this CMB Bharat consortium and joined the effort. In April 16, 2018, we submitted this proposal exploring cosmic history and origin, a proposal for next generation space CMB mission for near ultimate measurements of CMB polarization and discovery of global CMB spectral distortion to ISRO. This was the rough design of the of the satellite, with a total weight mass of 2 tons, which actually fits well under the capacity of our geosynchronous launching vehicle Mark III in the second Lazarus orbit, with a diameter of 4.4 meter and a clearing height of 4 meter. Our main goal was very similar to Core, and to have the energy of to find the energy scale of inflation by constraining the primordial gravitational wave, find neutrino mass, total neutrino mass, find reionization optical depth to a cosmic variance limit, then also to probe smaller scale physics. And we proposed it to ISRO as a joint ISRO-ESA mission. These are the primary science goals, which I already said. Complementary science goals are as follows. We can have cosmic infrared background analysis, magnetic field of the Milky Way, dust, and magnetic dipolar emissions, etc. So the time scale was set to be 2035 and 2040. So we gave 3 options as the possibility of this mission. For example, the configuration option A is just the imager, polarization sensitive imager with nearly 2,400 detectors spanning the frequency range between 60 to 900 gigahertz, and with a target CMB polarization sensitivity of 1.7 microkelvin arc minute. Option 1B uses more optimistic technology. For example, we propose that we can use dichroic pixels in test bolometers, and we can pack as much as 3 times than the option 1A, and it brings down the sensitivity from 2 microkelvin arc minute to 1 microkelvin arc minute. Again, this is ambitious, but doable with dichroic pixels. The option 2, the third configuration that we proposed, is to have a Fourier transform spectrometer here to detect the CMB spectral distortion with 3.6 degrees beam size, 12 gigahertz frequency bandwidth, and frequency range covering 36 gigahertz to 3000 gigahertz. Here are the comparison of sensitivities starting from Kobe. So we have detected these 2 lines, 2 anisotropy power spectrum, temperature and E mode. We of course detected the B mode from the B mode, the lens, but it is not the primordial B mode that we have detected. We have detected the lensed B mode from the E modes. So different noise CLs are given here. For example, WMAP was here, Planck is here, and the light bird around that time, what it was proposed around our time, was here. As you can see, the light bird is also ambitious to detect the CMB B mode anisotropy, primordial CMB B mode anisotropy, if it is of the order of 10 power minus 3. The tensor to scalar ratio is of the order of 10 power minus 3. But it does not go to small scales. So you cannot get much information about the neutrino physics, dark matter physics, etc. So it basically truncates at L equal to 900 or so. And the CMB Bharat temperature and polarization sensitivities are given here. From the larger scale to small scale, it can cover like that. So these are the few analyses. So for example, what you are seeing in the blue contour are from the CMB Bharat ECHO proposal projection, and this was the then Planck constraints on spectral tint and tensor to scalar ratio. As you can see that we are using low TeB from Planck because around that time in 2018 beginning, Planck did not release their low L polarization data. So the constraints are not that good in reionization history physics. So this is for the NSR plane if you allow to vary the NT, if you do not follow the inflation consistency relation. So the bottom line is that we can detect R of 10 power minus 3, tensor to scalar ratio of 10 power minus 3 at 3 to 5 sigma. These are the constraints on running and the slow roll parameter. These are the 2 Hubble slow roll parameters. We'll be able to detect the tau with a delta tau of 0.002, which is the cosmic variance limit for simple monotonic ionization history. Again, as you can see that there is a degeneracy. I think Subodip was slightly hinting towards that. But if you are using low LEE data, you do not see this degeneracy panning out like this. It actually breaks down because of the CMOL likelihood constrains the tau pretty well, and it breaks the degeneracy with lensing with the high L. Okay. It can detect neutrino mass at 3 sigma if some of the neutrino mass is 0.2 electron volt. We used it as a Ferruccian model. The effective number of relativistic species we can detect with a delta N effective of 0.04. we'll be able to improve omega k constraints by a factor more than 4 times. And if we are talking about new physics, it can detect also new physics beyond lambda CDM at more than 3 sigma if the Hubble tension persists. Here, for example, as a representative, we have used this CPL model, and we showed that even if we allow for the omega k variation, even if we do not know the geometry, we can actually see some hints of dynamic dark energy at more than 3 sigma. Definitely for different models, it will be different. For dark matter annihilation, from the present constraints or the then present constraints with Planck plus low TeV plus lensing, we can get constraints with by more than a factor of 4.5. This was a work by Shubhadeep in 2018, and where they talked about photon to axion-like particle conversion, and this was from the spectral distortion. If you put the per channel spectrometer sensitivity here, and if the polarized axion has a signal in the spectral distortion at this level of the order of 10 power minus 24, because the per channel sensitivity is of the order of 1.2 into 10 power minus 25, you can detect such effects. And here are the mu distortion and y distortion plotted as a to show the scales.
What's the polarized axion?
So he can talk about that. Probably he's the best person to talk about that. From the gut.
It's a pseudo-scalar particle. It can't have polarization.
No, it's a Primakov effect. Primakov effect depends on magnetic field.
Yeah.
And if you take away photons which is parallel to the magnetic field, the photon you see remains to be polarized. That's also black body CMB component which is parallel to a magnetic field direction gets eaten up into an axion.
Axion conversion to polarized photon. Okay.
It's a photon conversion to
understand.
axion.
That was not obvious.
Not that way.
Okay, so so these are the developments over the last few years. So we, as I said, that we submitted this proposal, and in April 2018, it was highly appreciated by the ISRO's highest science advisory body. However, ISRO wanted to have a higher share of responsibilities for payload. For example, we are asked to see whether we can build the detectors, etc., here in India. During pandemic period, there were major structural changes in the ISRO, so I'm not going into the details of that. But ISRO wanted to focus on space sciences, planetary exploration, etc., and to increase the boundaries of Indian capabilities. Early 2024, this Apex Science Board of ISRO, which had taken the responsibility from the ADCOS, initiated a space science roadmap formulation, SSRF. They created 6 splinter groups created to identify space science missions or goals. And CMB polarization mission was identified in the splinter group 2. I'll take 2 to 3 minutes, that's it. In the cosmology and gravitation session. So in June 2025, we submitted the proposal again, updated proposal, and it was identified as a prospective mission in 10 to 15 years. Parallelly, ISRO Space Program Office tasked Tarun Swaradip to develop a roadmap to CMB polarization mission within 2035 to 2040 to mainly identify the key instrumentation needs, understand the developmental challenges. This is what we are working now, and chart a path of expertise development. In July 25, some of us met in a national cosmology meeting at my institute, IMSC Chennai. And recently, we are talking to Indian experimentalists or instrumentation experts from IISc, IIT Kanpur, NICER, PRL, and RRI, and few other places for the detector, mirror, and cryogenics development. There has been good feedback, and we are planning to have a joint meeting with a Netherlands-based research organization in January to see the possibilities of collaboration with them in the detector development in particular. These are the sectors. For example, in the focal plane, we are looking for either transition age sensors, which are widely used in ground-based observations, TES detectors, or MKIDS detectors, which are relatively new, but the antenna coupling technology is less mature, which is needed for, as I understand, for having the dichroic or trichroic pixels. These are the institutes that can be potential centers for this development. For cryogenics and mirrors, we need detector cooling at 0.1 Kelvin and reflector cooling at 40 to 100 Kelvin. So IIT Kharagpur, IITM, can be the laboratories. We are trying to identify the laboratories where we can develop this kind of facilities with definitely international collaboration, and silicon carbide mirrors we are hoping to get support from the LEOS ISRO centers. These are the present timeline or goals that we are planning to have. That the short-term goals actually is to have a study phase. The long-term goal mid-term goals are for the detector development. This is up from 2031 to 2035. So, and 2035 to 2038, we are hoping to have the launch, and the data collection and analysis will be up to 2045. So these are the two works that Tuhin, Ghosh, and Tarun Saurabh have done for the CMB Bharat forecast, in particular in the B mode polarization, and Tuhin is going to talk about that. So finally, I would like to keep this slide as the final slide, that the CMB ground-based observations, for example, ESO, will be crucial for small-scale. Lightbird timeline likely to get pushed for the next decade because of this reformation triggered by KEK's decision to pull out from there. Fossil, another recent proposal led by Nabila Ghanim in E8, the European Space Agency's joint mission, is selected for phase 2, which is for the spectral distortion, has similar goals as the ECHO proposal. And in the meantime, we would like to get a study phase approval from agencies for ECHO. So with that, I'd like to finish. Thank you.
Hi, thank you for the nice talk. I wanted to ask about the CMB Bharat. It's very nice, but there's a lot of similarity to talks from Tarun Saurabh that we have heard in the past. I just wanted to ask, what if we face same situation from the funding agency? What's your plan B?
For the plan, what is the funding agencies? Sorry, I don't get the...
I think in the past it has got a pushback from...
It did not get a pushback. We were asked to identify the labs to build the detector technologies. It is not that the funding agencies, ISRO, is going to give money to someone to build the detectors elsewhere. We are trying to have the capabilities, to build the capabilities in India, so that we can develop technologically as well. So it was widely appreciated, but at the same time, we are advised to identify the places where we can build this expertise, build the detector development, etc. So that is presently what we are trying to do. Definitely, there are competition with Lightbird, but we have slightly different science goals as well. Okay, Tarun Saurabh wants to add.
No, I just wanted to say.
Yeah.
I just wanted to point out that in both Lightbird and Fossil, a number of researchers from the CMB community in India are involved. I mean, so it's not as if this is happening totally as a separate exercise or anything like that. So it's just the building of a community which is important, and the prospects of what all can come up within India. I mean, he's been talking about detectors, but detectors may not be the thing really to gun for. I mean, it is something that may not be the things that will fly.
Yeah.
But this gives a reason for development in those areas.
Yeah.
And I think what I should also point out is there's interesting developments on the ground. So ISRO is setting up a 6-meter telescope in Hanle with at least 230 gigahertz and 350 gigahertz and maybe a couple of lower frequencies. This is for different science, but I'm sure that is going to feed into the joint thing, and that's funded.
A comment or two. I think it's absolutely fantastic you guys are doing this. I think we all hope there's another satellite in the future for the CMB. I'm not quite sure I'd sell it the way you have. One of the huge benefits is you can just do things from space you can't do any other way, just period. And it's that frequency coverage.
Yeah.
And I think that's just number one by far, because what will happen on the ground, I think, is there'll be tons of cross-checks. There'll always be systematics down to 3 sigma of your noise for any satellite as well.
Yeah.
Right, so I think that you can get all sky coverage, which is huge. You have this incredible frequency coverage,
Yeah.
and
Yeah.
yeah,
Beyond
it's
200
fantastic.
gigahertz, yeah.
Yeah, yeah. So, good luck.
Any more questions?
I mean, to Tarun and everyone, is it open for international collaboration?
Our proposal explicitly said that this will only be done in international collaboration. The point was to enable. The impression I was given is ESA found, there were not enough international partners or money coming in. I say this at the risk of, people like, I mean, India is not resource-starved by any stretch of imagination at this point. You have to pitch things right, and also you have to play the game right. I mean, you have to train, you have to give enough time. But we can be very, very, significant partners in, so I'm not personally, I would honestly say, I mean, it doesn't matter who launches what. I mean, that science goal has to be met, and India has a far larger community than what it was in 2000, which was almost unit. And so I think we should step up and, contribute. That's the thing. Shouldn't be one group in Planck kind of a situation. So it isn't.
So what are you think the chances that the spectrometer will go in? Because it looks like Lightbird does only the beam modes, and Fossil only does the spectral distortion, and here you're saying you might have both. So what's the? I mean, of course, it's a cost trade-off issue, but
yeah, we had given the cost estimation only for the option 1A. So we.
All three. This goes up by $400 million.
Okay.
So it's
okay.
B plus, so best imager plus spectrometer is $1.2 billion 6 years back. And only spectrometer at the best level is $400 million, cost 6 years back.
No, the
So that's the number.
6,000 crore one?
No, only spectrometer. So we have a definitive good science case, and first since Kobe to go make a spectrum measurement of cosmic microwave background, and it will cost us about $400 million to get it at the sensitivity Dhiraj mentioned just now. Alone, that's right.
And the imager alone?
800.
Yeah. The imager alone was 6,000 crore, which converts to nearly at that times $800 million. That's right. So 400 is adding to this.
400 is the FTS spectrometer.
Yeah.
Since instead of capabilities with respect to Fossil, the spectral distortion part is comparable? Or?
Comparable. Fossil goes from 30 to 2,000 gigahertz.
But Fossil won't go to mu distortion.
Yes.
Fossil is aimed only for thermal Sonia-Zeldovich.
No, mu 2 to 10 power minus 8, it will be.
We will detect
at 4 sigma.
distortion.
At 4 sigma.
CMB Bharati flies with the imager is targeted to achieve mu distortion. It's a definitive science case.
Yeah.
I mean, so for people who are balking at these numbers, 1.2, I mean, my justification, I got a lot of pushback because our proposal added up to many times the other proposals together, and that was pointed out. The point I made was ISRO never put a cap. So that's a lesson for them, that you have to tell us where to stop. But we were careful to say, you can do this much, and also the sharing. So obviously, if it was a 1 billion thing, we always said, we had points of contacts in the science community in Europe as well as US mentioned explicitly who, if ISRO was interested, they could be the ones who would take it forward and try to see if we can get talking. I think since 22, I mean, after coming here, I was very surprised that it was still, and it was just, not clear what is happening, but now at least there's some, some definite things to do. So they are looking for some definite plans. And in terms of money, I don't think in terms of the scale of the money, I don't think that's the major problem. I think that we are expertise limited, largely, extremely expertise limited. Huh? Yeah, so we, no, not officially. I mean,
Can it basically be any negative thing for the same border? They said, oh, you are involved with that, so you want to go to your own?
no, I mean, we are, at this point, I think the proposal writing, there must be 6, 7 of us who are signed up. And, I don't even know if I'm signed. I don't. But there are people who actually work on this, and they're signed up, and a lot of good, so I think it's already clear that anything that goes forward, there'll be sizable contribution from India in the science. But the
should have a very clear difference agenda for the politicians to probably the more proposals to do it, the better, right?
So
no, I mean, I don't think it is on or off kind of a thing, like fossil is on. I mean, one strategy could be to wait till, say, 2030 or something. I mean, in my mind, we just get going with something, right? We are participating in fossil, we are participating in any proposal that is coming up, because that's itself is a part of the training that I think we as a community need. And maybe 2030 is when we look at, how far did Lightbird go? And Lightbird plus ground, is it going to be enough? I mean, I think we'll have a fairly good idea of, what's the final configuration of Lightbird that flies, what is it that it will do. So, but, I don't want to wait till 2030 to start. So we need to start things going now. And then, anything that we are doing is useful to the country. I mean, I think there's no doubt in my mind about that. Any of the technologies, and India is pouring a huge amount of money in, the kind of things, chips and all, but these are decades away. I mean, they want results in 5 years, that's not going to happen. But,
So there's one last question. Yeah, right.
If this last question is okay, I didn't want to interrupt the political discussion. I had a question about the foregrounds. So you made a prediction on constraints on R of 10 to the minus 3.
Yeah. So foreground Tuhin's talk is going to be, he will be talking about the 2 papers that I flashed in the last penultimate slides. So he will be talking about the foregrounds for the CMB Bharat. One comment on this fossil. We have recently talked in the fossil meeting as well. So they are also interested in the CMB Bharat's capabilities, and we have been contacted by agencies working within the fossil to in the collaboration in the detector sector.
All right.
Thank you.
Thanks very much. Tuhin.
No, you can just go to the HDMI.
Okay. So the next talk is by Tuhin Ghosh, and he'll be telling us about B-mode forecasts from CMB Bharat.
Next slide is not going. Okay. Or we can just do here. It's okay, I can just do here. Okay, good afternoon everyone. So my name is Tuhin Ghosh. So I will talk about B-mode forecast of CMB Bharat. So before I start, I'd like to thank the organizer for inviting me to give this talk here. So the stage is set by Dhiraj, who will talk about ECO and CMB Bharat. It's the same thing, basically. So So the question is, when we wrote the proposal, we said that we will achieve sensitivity of R, which is 10 to the minus 3 at 3 sigma significance level. When we wrote the proposal, it is just, we take the number from Planck and we scale it to that, by scaling the noise sensitivity to achieve those numbers. So we want to basically go back and look to do realistic simulations. So from Planck, we have a lot of information about the foregrounds. So we can add CMB foregrounds and make the foregrounds more complicated and see if we can achieve this, whatever we wrote in the proposal, actually, using the standard component separation method. So the idea is that we can explore this frequency range, what Lyman said, and see if this frequency range is enough with the existing component separation method, or we need develop new component separation method. What are the challenges? So that is the main question, and whether some way we can reduce the cost. So we have more frequency bands. So this frequency band is not just to do cosmology, but also to do galactic astrophysics and extragalactic science, like CIB, dust polarization, magnetic field. So whether we can cut down those high frequency bands and see, whether for the cosmological inference, whether it makes any difference or not. So that is broad goal of my talk. So there are 2 papers that we wrote on forecasting of CMB Bharat. And just a quick note that some of initial slides are same as Dhiraj, so I will just go quickly over them, not to bore you. So basically, these are the space-based experiment every 10 years, so Kobe, WMAP, Planck. And after that, there are 2 experiments which are planned stage. One is Lightbird, which is supposed to fly in 2032. And then from Indian side, we propose the CMB Bharat mission, which is in the time scale of 2035 to 2040. So the main goal of this experiment is to measure the B mode over the full sky, so that if there are foregrounds or there are systematics, we can control them. But from the ground, there are a lot of efforts going on. So there is a Simons Observatory, SPT, BICEP. So they keep on collecting the data to say anything about primordial B mode. And they're putting, like for BICEP, when they combine with WMAP and Planck, they're putting tighter and tighter constraint on the measurement of R. So why space mission? So if you can do everything from the ground. So basically, the CME measurements has been transformational for cosmology. For Planck mission, it measures all the information from the CMB temperature, but there is a lot of information that need to be extracted from CMB polarization. And since Kobe, there is no spectral distortion experiment. So recently, fossil was proposed. It was in phase 2. So if you have both in a proposed mission like CMB Bharat, it will be helpful to nail down the CMB polarization and also to do spectral distortion. So there are high scientific promise, like it reveals the signature of primordial gravitational waves on inflation. There are high goals like neutrino physics, number of species. We can map dark matter distribution through lensing potential. We can reduce the error bar, which is the legacy results. There are a lot of galactic astrophysics, science, and extragalactic astrophysics we can do. And there is an unexpected discovery space, which is coming from CMB spectral distortions. So this started from 2018. Dhiraj already mentioned that. So we proposed this in 2018 as a CMB Bharat consortium. And last year, there was a meeting called by ISRO where they make this separate groups, and CMB Bharat is still in their priority list. And this year, there was a meeting. So we are just collecting experimentalists who can help in setting up the CMB Bharat. So basically, what we are targeting is near ultimate CMB polarization survey, which noise sensitivity is 1 to 2 microkelvin. So there are 3 configurations, which was mentioned. So with a more number detection, like 6,000 plus detectors, we can achieve to this 1 microkelvin sensitivity, and possibly spectral capability to measure the CMB spectral distortion. And the idea was to first work in a survey mode for 4 years, and then work in an observatory mode. So if people have a targeted object, they can write a proposal and look at like the high frequency channels, which are more sensitive for a target observation. It's like Herschel plus Planck kind of thing. So this is a new science, lot of science. Dhiraj already mentioned that, so I will not go through it again. So this proposal is, when it's written, is in collaboration with other international collaboration, taking into account the full costing of the mission and launch. And the other PI, like CORE and PIXI PI, are in part of the international point of contact in the proposal. Okay. So, so basically, what LightBird does is it has a limited frequency coverage from 40 to 400 gigahertz. So we go bit below and bit higher, and it has a more noise sensitivity. So we can go up to like 1 arc minute, which is we can probe those small scales. So it is better than LightBird in that sense. And we are talking about sensitivity of arc, which is 10 to the minus 3, and basically the signal is much below the foregrounds. So there are basically two foregrounds which are dominating for the polarization measurement. One is the synchrotron and one is the dust. So foreground is basically the main challenge, and we want to see if, in case of realistic foreground, what we learned from Planck, whether we can recover back what we claim. In simple case, simple foreground scenario, it works, that is expected. But if you make the foreground complicated, how does it perform? So just quickly, this slide. So basically, we are targeting R of 10 to the minus 3, assuming there is a delancing. So in future, we can do internal delancing or delancing with CIB up to 70% to achieve this target. So this, when we wrote this 3 sigma detection, it is assuming that there is a 70% delancing we can do. Okay. Sorry. And then we can measure this parameter with higher accuracy, and it will shrink basically the error bars. And then there are a lot of galactic science, what we can do from this. So basically, there are two designs. One is focal plane 1A and 1B. So 1A has goes from 60. So this does not go to very low frequency. So synchrotron can be a problem. So it has 2,400 detectors, and the other one goes from 28 gigahertz. So it can it's like similar to Planck, like 30 gigahertz. So it can somehow controls the synchrotron contribution. Sorry. Okay. So this is all about CMB Bharat. So let's come to our work. So what we do is we take this focal plane 1B configuration, which is more optimistic. So it goes from 28 gigahertz to, so somehow it is, I'm not touching anything. Okay. So it goes from 28 gigahertz to 850 gigahertz with a noise sensitivity of 1 microkelvin per arc minute. So in this CMB Bharat collaboration, we identify some people, like some students, like Devabhrata Adak and Aparajita Sen. So they are a student. And with international collaborator like Jack Delabury, James Martinez. So we try to see, using the standard component separation method, if we can achieve this sensitivity or not. So that is basically published in this Adak et al. 2022 MNRS paper. So what we learned from Planck is that foreground is a major challenge for this CMB B mode detection. So Planck intensity, we can see the CMB map. So if we mask the galactic plane, more or less we can extract the cosmological parameters from this map. But the polarization maps are totally dominated by foregrounds. So there is no frequency where we can just, or the clean frequency or clean angular scale where the CMB dominates. So we want to put all this information to simulate the maps, which is more realistic, which is driven by the Planck foreground model. And then we want to test our component separation method. So, so this is the picture taken from Simon's Observatory, like 2020 paper. So what we have is from Planck bicep, low L information up to like a degree scale, up to L is equal to 200. And what people do is they take this empirical model and they just extrapolate to higher angular scales, assuming that this works. Okay, but it's not that there are only two major foregrounds. There are other foregrounds which can be dominating, like the CO emission. So we don't detect it yet, but in future it can have a small clumpy natures and it can show up in this scale. So for time being, we can make our foreground model simple. So we can take only two foregrounds, dust and synchrotron. We can add like AME, which is also not detected. So we have upper limit from AME and the point sources. So the idea is that we use this model with a not directly the power law model, but maybe some like physically motivated model which satisfy this power law thing. Okay. So just a few words about what are the different kind of polarization. So one is the synchrotron polarization. It is produced by this relativistic cosmic ray electron, which is accelerating in the galactic magnetic field, which is order of few micro Gauss. So this is dominating at lower frequency, and usually it can be modeled with a power law in Q and U. And it can be polarized up to 70%, but the observed polarization is typically like 20%, and at max it can go up to 40 and 50%. So this is usually dominate at lower frequency, and we measure this spectral index to high accuracy, like minus 3.13 plus minus 0.3. So this is one foreground which is dominated at lower frequency. And then there is at high frequency, these are dust polarization. So these are small aspherical dust grains which are precessing around the galactic magnetic field. So these dust grains are absorbing light in extinction, and it emits in emission. So with this dust, it can be, what is found that it is like 20% polarized. So people earlier expected that it can be, at max, can be polarized up to 5%. And they follow modified blackbody spectrum. So we have two components. One,
magnetized dust.
I will come to that. So we, for polarization, we only focus on the synchrotron and the thermal dust. So the magnetic dipolar emission is.
For the B mode, that will be important.
Yeah, so we introduce spinning dust, but not the magnetic dipolar emission in in this formalism.
But is that not important for B mode?
This is not detected, and we don't know what is the upper limit on the magnetic dipolar emission.
When the sensitivity to which you want to go,
Huh.
it may be important.
Okay.
You don't agree?
Yeah, we can talk. Okay. So, so basically, given this Planck information, so if your target sensitivity is say R 10 to the minus 3, so what we found is that dust and synchrotron, they are much higher than the signal that we are interested in. So this is the L dependence, and we also have the frequency dependence. So basically, there is no clean frequency space or the multipole space where we can detect this R of 10 to the minus 3. So anyway, we need to deal with the foregrounds, and for dealing with the foregrounds, we need to have as many frequency channels as possible. So more frequency channels is better. So it will help us to clean the foregrounds, or it will help us to understand or model the foregrounds better, so that we can clean this up and reach to this sensitivity. So that is our goal. So foregrounds are much higher. It's like in 21 centimeter, the foregrounds are much higher. And we want to clean this to get this 21 centimeter signal. A similar situation in this B mode analysis. So what people do is, there is something called commander approach or like a Bayesian approach. So what we can do is whatever data we have, we can model as a combination of CMB, synchrotron, dust, and the noise. We can fit with a modified blackbody spectrum for the dust, power law for the synchrotron, and we know that CMB follows blackbody spectrum, so it can be accounted for this A factor. So this is what is done in the Planck collaboration also. So they fit everything in a Bayesian way, so that if once we get a CMB map, we can know what are the different components, whether they follows the usual statistics or not. So what is shown in this paper by Matthew Ramazé, that this model-dependent thing is good, but suppose you don't know unknown things. So something which is not detected by Planck, which is at lower sensitivity, say magnetic dipole emission, or if dust, because our requirement is we need more frequency coverage. So it may be that it does not follow modified blackbody component, single modified blackbody. It can have a two-component dust model. So if you model with a wrong model here, it will leak into residuals, like the foreground residuals. It mimics like a signal. So suppose we put R of 0.05, but we will detect some signal which is like 0.08. So suppose it is 0, we will find some detection of R. So I think that is not correct. So this model-dependent way is good to cross-check, but we should have some blind approach where we don't assume anything about the foregrounds and try to get a map which will tell you that this is the value of R. So this was the original idea in this paper, Kataya and Komatsu 2011. So if you have 3 frequency channels, say they have a toy example, like 60, 100, and 240. So one is dominated by synchrotron, one is dominated by dust, and one is dominated by synchrotron. So we can take this 2 frequency and just extrapolate to 100 gigahertz and subtract the dust and dust and the synchrotron contribution, and we can achieve this target sensitivity of 10 to the minus 3. So this is how Lightbird started, and then people realized that with this 3 frequency, we cannot do this, so we need more and more frequency, and then now it basically covers from 40 to 400 gigahertz with a lot of frequency channels. For pixel, if you want to do this, it will be noisy. So we can collect, instead of doing in the pixel space, we can do this same thing in the harmonic space. So this is a model-dependent approach, or you can say likelihood approach. So this is what is done in the bicep analysis. So they take the, whatever, 1% of the sky they have, they compute the power spectrum, and they take all the WMAP, Planck, their frequency, they take all the available cross power spectrum, auto power spectrum, and they model it with this equation, assuming that the dust follows modified blackbody spectrum, synchrotron follows power law. So these are 4 parameters. And then when we go to the harmonic space, the synchrotron and dust will be correlated, which is captured by this parameter rho. So this synchrotron and dust, they are basically originating polarized dust and polarized synchrotron, originating from the same underlying galactic magnetic field. So at large scale, they are correlated. So they have these 5 parameters, and then they fit 2 extra parameters, one for R and one for lensing amplitude. And with 7 parameters, basically they are targeting this R measurement. But what is the guarantee that this model is correct? Because if one pixel it follows a modified blackbody, each pixel, if there is a spectral variation. So when you average them, it's not necessary that some of the modified blackbody is also a modified blackbody. Okay. So currently, there's no evidence, strong evidence to go out of this model. But when we are targeting for 10 to the minus 3, it may be this model is not correct. So we need to include the higher order correction. So this is something called movement approach, which Jens Schulba pursue this. So if you have more frequency coverage, we can put these higher order corrections to account for spectral variations.
But what if the background has the same spectrum as the blackbody that you're looking for? That is the issue, right?
If it is same,
similar within your resolution over the limited frequency range.
So
and that is the case for magnetized dust. That's why I asked.
Yeah. So
then how do you ever separate it out?
No, it's to be slightly different. Like if it is 10 Kelvin and 2 Kelvin, if you have more frequency coverage, then we can distinguish.
What I'm asking, at the level of sensitivity for the B mode that you're aiming for, can you be sure that you can exclude the possibility of even a subdominant component of magnetized dust, which is a similar spectrum to the black body, over the frequency range you're looking at? That's a worry, right?
Yes, but we do. But my point is that we don't know how much it is polarized, like how much it will affect. But once we have the measurement, we need to be careful about other components. So we are not using this. So we will use the blind component separation. So we will use both this method and the blind component separation to make sure that when we say if some components are fainter, how it affects this 2 methodology. So that is like the exercise we did. Okay, so this dust synchrotron correlation comes up in the Planck data. So it just shows up in low L, but not at high L. So all these things are usually modeled in the L space, but this row we can measure directly from the data, but it does not have a very particular pattern. So this thermal dust amplitude, it follows power law, power spectrum. The amplitude of synchrotron is also follows power law, power spectrum. So we can fit this data. But here it has dominant at low L, but not at high L. Okay. So we need some kind of model or some better data to actually understand how these different components play a role in this model fitting. Also, on top of it, there is something called dust decorrelation. So what is assumed is that what we measure Q and U polarization, it is just scale version from one frequency to another. It may happen that the polarization direction, it will rotate with the frequency. So it was shown in this paper, Tassis and Pavlidou. So if there are two dust clouds with different temperature, different emissivity, so in polarization, when we combine them, there will be this ratio. It's not 1. It should decrease with 1. Okay. So in earlier analysis of Planck in 2016, they found very strong evidence of this in the data. Later on, it was found that it is mostly dominated by systematics in the Planck data. But this is something which is worrying for the component separation. So if there is a dust decorrelation, so we don't know we expect it to be decorrelated, but how much decorrelation, what is the L dependence, what is the frequency dependence, so we don't know this. So that is another level of complexity. So we can make this foreground as complex as possible and see how this method works. So, what we did is that from the dust spectral index variation, so it's not a one number, so it has some variation. And if this spectral index is same for intensity and polarization, we can model this dust decorrelation by this factor. So this is one way. If there is a spectral index variation, it can be modeled using this relation. But if the polarization angle changes, it cannot be modeled like this. So with this extra one parameter, delta D, from the Planck joint analysis fit, we found that when we go to lower and lower sky fraction, it increases. So basically, if there are in the line of sight, if there are 1 or 2 dust clouds, the effect is more. If there are a lot of clouds, it will just average it out and it becomes like 1. So, if you have full sky mission, we can safely assume that it is close to 1. So it's not a problem. But for other ground missions, when you're looking at smaller sky fraction, it can be a dominating thing. So it's not necessarily like to be 5%. It can be even if 1 or 2%, it is a problematic thing. Okay. So, we need some model to model this decorrelation. So what is done is that suppose we are here, 8 kiloparsec away from the sun, and we see this different line of sights. And if there are dust cloud in different locations, we can just, with a different emissivity, different spectral index, if we can just integrate this, we can make a model which will reproduce the statistics of the Planck. It's not exactly power law spectrum, so there will be some jiggle. So this is what we did in this 3 papers. So so you can see this is the model which are different components of the dust in cold phase, thermally unstable phase, and warm phase. And we can basically reproduce the statistics of TE, EB, and E. So this somehow these models will produce decorrelation. So if you scale this model from one frequency, another frequency, it produces this 1 or 2% level of decorrelation there. Okay, so we have now this model. So then we put this together with a CMB with a thermal dust, where the thermal dust is just a scale version of dust from one frequency to another. We include this line of sight model with 3 dust components, which includes decorrelation. So it includes some 2-3% decorrelation. There is a Giants dust model which is constructed from dust extinction map. It will have very less, it's like 0.5% decorrelation. So we have these models, and then the synchrotron, which can be more theoretically motivated, like Galprop model, or there is a power law or curved power law. We put this in the simulation. So we make this different combination of foregrounds. We add CMB, we add noise, which is expected noise sensitivity from CMB, and try to see what we get. So these are basically different models that we put, set 1A, 2 ABC, and 3A. So we go from very simple model to very complicated model, and we ask the question what we recover back. So for that, we need two component separation. These are very standard methods which are used in Planck collaboration. One is the knitted ILC, and one is the commander method. So one is the Bayesian multi-component spectral fit. So you know the energy distribution, spectral energy distribution of each of the components. Other is just a minimum variance estimator, so it does not assume anything about the foreground. It is just minimizing the variance to get to the CMB. And our goal is to detect primordial B modes, so we don't need very high resolution. So we worked with like 60 arc-minute resolution, like 1 degree beam at n side 256, just to make the computation faster. So what we find is that, so this is the result. So this B mode forecasting. So our R is 0. So we apply this needlet and the commander method. So commander is the model dependent. So if you have the correct model, it will model it anyway. So we get a value which is close to 0. But when we add more complexity in the foreground model, so like set 2A and 3B, so this has decorrelation. So this is not included in the model fitting. So what is found there that, so it will give you very high values. So it is 0, but we get order of 30 to 50 times 10 to the minus 3. So that is, yes. So that is kind of problem for commander method. For needed ILC, which is a blind method, somehow it knows that this is foreground, and it try to minimize this. So we get close to 0, but it inflates the error bar. So it increases the error bar and account for this foreground complexity. So any unknown foregrounds, so needed ILC is well equipped to do that, but the model dependent approach we need to be careful about. Okay. So this is just the numbers, but we can see this in this plot. So basically, so 0 is the value, and all these points are deviating for the commander. So like commander, if there is a curved power law, so it is not exactly power law, it is curved, but in the model, we put a power law. So the curvature, what we put is constraint from WMAP. And the commander, it somehow gives the biased result, which needed ILC does not give. So that is basically the take-home message is that we should not rely on one method. We should rely on multiple ways to make sure that we recover the same CMB or the same value of R.
Because you're modeling the synchrotron by Galprop, right?
Yes.
It's just a slab. It's like a hamburger. So it cannot match high ends. It can only match the low end. So you have to add other components to it to match the angular power spectrum of the radio background.
Right.
So there is a obvious some piece missing there.
Yes, and also we did different combinations. Like we put a Galprop model and fit with a power law thing in the commander approach and see like how well it does.
Actually, you can fit the angular power spectrum of say the Hazra map pretty well by just 3 components. So
yes.
Galprop will pick the lowest ones. At the smallest scales, you have interstellar turbulence. And then in between, you have to add in old supernova remnants. It gives a match good to about 3%.
But this Galprop model is based on in the frequency domain, not in the L domain.
So you have to do both domains.
Yes, yes, yes. Okay. So ultimately, this is the like summary of this analysis. Is that suppose our target sensitivity 10 to the minus 3, we can achieve this in case of very simple model of foregrounds where the synchrotron follows a power law spectrum, the dust follow modified blackbody spectrum. So if we can delens it like 70%, we can achieve this. If we just don't delens it, it will be like 2 sigma level. So from the commander algorithm, if we apply this to the simple setup, we need this lower frequency. So 28 gigahertz is not enough. So we need to get a handle on the lower frequency to properly control the synchrotron spectral energy, spectral index characterization. And this dust decorrelation is problem for commander kind of method because it just put it will put all the foreground residual in the CMB map, and it will give you bias estimate of R. So this is just purely due to the model mismatch between the data and the simulation. Okay, so this is, so given this it works. So now we ask another question. Instead of using all this frequency, 28 to 850 gigahertz, suppose we restrict to say 28 to 190 gigahertz or 28 to 340 gigahertz. So we don't go to higher frequency. So higher frequency means higher cost. So some way if you can reduce the cost, because our target is to measure the R. Okay, so for cosmologists. So this higher frequency is mostly important for people who are doing galactic astrophysics, like to measure CIB, dust magnetic field. So these are sensitive, this is good. So a lot of ancillary science we can do. So we group them into these different categories. So baseline, 28 to 190, so like a ground-based, like it goes to 200 gigahertz. Or 340, like the Planck mission, or the Lightbird, which goes to like 400 gigahertz. Or we can go up to 857 gigahertz and see like whether it can make much improvement or not. So, so we did not touch the synchrotron part, so we put a power law there. But for thermal dust, we use this HD dust model, this Hensley and Drain model, which is more physically motivated, but they don't have much decorrelation there. The GNILC dust map, which is this extinction map over the line of sight, and this, GNILC is the Planck dust map, and this MKD is constructed from the extinction map, which has decorrelation. So to quantify how well the component separation is doing, we look at this residual foregrounds and the residual noise. So we apply needed ILC method. So it basically gives each frequency channel, each angular scale some weights. And since this is a simulation, we know this foregrounds well, we know the noise. So we can calculate what is the residual foreground in this final map, what is the residual noise in this final map. And from that, we can see like how they are contributing, at what scale. So this is what is shown here. So we have these three models, M1, M2, M3. So when the model is simple, the foreground residual is less. When we go to the more complicated model with the dust decorrelation, so it is similar to the signal that we are expecting. So this is the B mode signal, and this is the mass we use, so from 30% to 60% of the sky. Okay, so this is like with a baseline configuration from 28 to 190 gigahertz. And then we start adding mode and frequency channels, like from 90 to 340 or 600 or 850, and see where there are improvement. So what we found is that if you go from 190 to 600, there is a drastic improvement. But after 600, if you keep adding channels, it will not make any difference in the residual foregrounds or the residual noise. So these are our figure of merits, or the value of R. So the R value or the sigma R, it does not change much when we start adding more and more frequency channels. So that is good for some other science, but not for CMB's like measurement of R. So basically, what we conclude in this analysis is that this frequency channel is not enough. So 28 to 190, we need to go up to 600 gigahertz to basically get a very good estimate of sigma R. So this is just from the needed ILC, because this is more, even with a complex foregrounds, it can deal with the fainter foregrounds emission. Yeah. So this is basically the summary of my talk is. So first we want to show that with realistic foregrounds, we can achieve this sensitivity or not. And we show that if the foregrounds are simple, we can achieve this sensitivity. Next thing is that we found that this commander method is not well equipped to deal with the dust decorrelation. So we need more data from ESO or BICEP cake. So in BICEP also, they do this analysis with and without dust decorrelation and see how their value of R changing. So that is, more data will at least help us to put us in a better state where we can know what is the frequency dependence, what is the L dependence of this dust decorrelation. And from this needed internal linear combination method, we conclude that what is the importance of this higher frequency band. So light bird, if it is stopped at 400, if suppose it goes to 600, CMB Bharat, when it goes to 600, it is better for foreground subtraction to go to the R value. Yeah, and thank you.
There's this other code for cosmic ray propagation in the galaxy called DRAGON, which also has a synchrotron model. Have you looked into how that compares with the GalProp one for your foreground modeling?
No. So we take the GalProp model, which is regularly used in the Planck collaboration for modeling the synchrotron emission. So whatever the standard.
Don't differ much in this respect. It's mostly DRAGON is mainly borrowed from GalProp.
Go ahead.
Thanks for your talk. You showed that the increased frequency range, or increased frequency range sampling, and the reduced noise does much better than Planck, which is great. And you say that you prove that by assuming simple foregrounds. But of course, the power of such an experiment is to also model non-simple foregrounds. I didn't understand 2 points. The first point is, in principle, Commander has the power to address pixel-to-pixel variations in spectra and an index, right? So you get the decorrelation if you falsely assume, well, you don't get to deal with decorrelation if you falsely assume that there's no spectral index variation over the sky.
But if the polarization angle is changing, so it's not account in this Commander approach. If there's a frequency decorrelation, like spectral index is changing per pixel, that Commander can take into account.
Okay.
But if the polarization angle is changing with frequency, so it will show up in the power spectrum, but it will not be captured in the Commander approach.
So Commander, in principle, can never address that.
But probably there will be some way mathematically they can take into account.
And then you mentioned the moment expansion method,
yes.
But you didn't seem to use it in your analysis, is that right?
So for moment approach, we need more and more frequencies.
More than you have here?
No. So it depends on like when you do the Taylor expansion. So how many orders you want to model. So for dust, there are 3 parameters in the first approximation. Now, if you go to higher orders, you like 3, like 9 parameters you need. That is just for dust. Then you have a synchrotron moment approach. So you need more and more frequency coverage, like more parameters.
I understand, but you did not use it?
No, because if there's infinite frequencies, of course, we can use it. But here we have like 20
there
frequency
are methods.
channels.
I mean, there's an extension of the moment expansion method that I think Susanna Azzoni, who was mentioned on Monday, worked on in the context of Leipert and SO. Or at least it was applied to SO.
I think they
recently.
stop at some like higher order terms. So they did not include all the higher order terms. So this have amplitude, beta, and temperature. So all you can take derivatives. So like
I tried out. I think it will work well. I think you got the channels right.
Shubham, did you have a question? Okay.
If you know that you need a handle on the synchrotron synchrotron, the way you have parameterized either in pixel space or in harmonic space, so why is it that there are no channels at low frequencies? I mean, 1B has 28 and 35, but if you want a good handle, you would like to have more channels in the low frequency end also. So the design does not reflect that. So why is that? Is it limitation?
Because the focal plane is fixed. So if you have go to lower frequency, you have a space constraint. So the detector size is more, so it's difficult to pack a lot of detectors in that focal plane. So that is the thing. And for ground, there are QOT experiment like from the ground in Tenerife. They basically target from 10 to 20 gigahertz. So basically, for those frequency, you can do it from the ground. But basically, you need a full sky map. So it will take, probably from the ground, it takes a lot of long time.
Yeah, full sky, you need full sky. So ground will not be sufficient for even.
No, QOT produce like almost like full sky maps. So southern
but they also have, I mean, because they are from different surveys, northern survey and the southern sky survey, so there will be some common calibration issues also. Even with Haslam, it's a patchwork, so to say.
No, but CBAS is doing like, they have 5 gigahertz, so they have a telescope, like Manchester, they have a telescope, and in the South Africa, they have a telescope. And they're looking at 5 gigahertz, and they combine this to produce a full sky map. So it is possible, but if you in the space, if one go you can make this, it is better.
Yeah, thank you.
Telescope is in South Africa, not in Manchester.
No, the northern one is in Manchester. No?
Northern was in Canada.
Canada, okay.
So what about free?
So free is not polarized. So we are talking about B modes.
Oh, you just care about B modes.
Yeah.
I see. And then the other question I had, so you were just talking about our galaxy, but there are other galaxies as well. So what about that?
So this cosmic infrared background,
well,
star-forming galaxies at higher
all,
redshift.
all the other galaxies that are outside have the same thing that our galaxy does.
So no, the resolution that we are working with, we don't detect like M31, M33 we can see in these maps. But depending on the orientation, probably it is the average it out. You don't see the net polarization. If you see face on, probably you see some polarization. But if it's edge on, probably not see any polarization.
Well, I mean, so those are words, but are there numbers that go with that?
So like CIB is one of the things that because they are oriented in a cosmic wave, so it will produce some net polarization. But we don't. What we have is the upper limit. We don't detect those polarization. So currently, it is not. Many things are not included in this setup. So like the CO polarization, CIB can be polarized, magnetic dipole emission can be polarized.
I don't know CIB because it's far away, but I mean, I'm just more worried about more local structures, local group, and I mean, things within 10 megaparsec, because those would give large angle effects. And it seems...
But if you just take the point source contribution to the CMB power spectrum and extrapolate it with, C minus 1 is, I guess, pretty small, which is the galaxies you're talking about. And you just nix a few of the other ones.
Yeah, I mean, I guess we're talking about large angle effect correlations, so I don't think point source, far away point sources matters. It's just things, I don't know, things within 10 megaparsec or a few, 20, 30 megaparsec. I mean, they have all the same things that our Milky Way has. So, so I don't know how big the effect is.
Prava?
So, Tarun,
Go ahead, Prava.
Tarun, sorry, not Tuhin, is there a reason why you do not look at the other component separation methods? SEVM and the fourth one.
So there are 4 component separation methods. So one is SNeIa, one is SEVM, which is template fitting.
Yeah.
Then this needed ILC and the commander. So we look at these 2. We do not look at SEVM and the SNeIa. So SNeIa, now the code is publicly available. Previously it was not available, so that this work was done in 2020, 2021. So that time we did not have access to that code. SEVM we did not try because it's just a template fitting. So you assume at one template like 353 and scale it to other frequencies. It's like similar to the model dependent approach.
Okay.
So all these methods are not fully independent. So some are like kind of correlative, but doing it in a different way, slightly.
Okay.
I promise I never will ask this question again. If you give me a direct answer, don't be polite, just say truthfully. So if there is the possibility, I'm quite serious about this, of a polarized foreground that over a limited frequency range can mimic a black body spectrum, you know what I'm talking about, and there was an indication of that, as you say, it was never detected, never established, but it could be there at about 20% of the full Planck fit that you did, I recall, over the entire frequency band, right? If it was actually there, I know you only have an upper limit, but if it was there at the upper limit, what would be your sensitivity to R that you can already deduce from the exercises you have done so far? What would be the limiting value of R you could detect?
We did not do this exercise, but depends on what is the polarization fraction, like how much it is polarized.
30%.
Then it is problematic for 10 to the minus 3. But if it's like 1% polarized...
The 30% is a theoretical estimate, but from a leading dust expert who you know, who was at Princeton. So it could be high.
Then it is really problematic.
So how you could go below R of 0.01? Could you go down to 0.01?
No.
Not even that.
No.
0.1.
10 to,
The current limit would be the thing. Okay, thank you. That was the answer I wanted.
May I add something on this? Yeah, so these all methods still assumes complete isotropy of the dust, our foregrounds. There are methods developed by Blake Sherwin and his students. I forgot his name now, sorry. Right, yeah, so which takes into account the statistical isotropy violation of the foregrounds. When you take into account those, you don't get into the problem at the level it is appearing over here. Just because foregrounds are not isotropic in comparison to cosmic microwave background.
It is true that this magnetized dust is correlated with the galaxy, that's true. But
And it has been shown. I mean, there were people in 2018, if I'm not wrong, right? So his tries to make this point of isotropy violation of dust and how it will show up.
I see, so you demand isotropy of the signal you're looking for, then how far?
You demand an isotropy of the
I understand the point. How much further can you then go by putting that constraint? Even if it was there at the 30% level. So if I say there was polarized, magnetized dust, polarized at 30%, just below the upper limit that was set by your Planck analysis, how low could you go in R by using this?
So that's what I don't know.
Angular information.
But basically, after this, there are a lot of work, like people develop.
Because detected towards LMC and SMC already, so the total amount in the galaxy is not known because they couldn't. You could include it in your fit, but what you're saying is that even if you exclude it, you still get a good fit.
Yes, there's no strong evidence of that.
You can't separate it. So in the first version of their paper, you'll find a fit including dust. In the second version, there isn't.
No, it was the data change.
No, exactly. That's a different dimension. Yeah. So then that is important to pursue that. That is the only way to do it.
Yeah, but the first version, the data was different. It's the next version, the data is different. So it's less systematic. So there was some systematics which goes over.
I'm saying that now looking to the future, the angular variation in the sky is an important discriminant.
You maybe can do it after the fact. You should separate.
Yes, okay.
Did you? All right, so I think the next session is a discussion session. So let's thank all the speakers and we can.
Thank you.
All right, since we're running 40 minutes late and everyone wants coffee, so discussion will be in coffee. And then we'll come back for Narlikar. What's the Narlikar section? 4:40 or it's supposed to start at 30 or 4? We come back at 4:30.
So this is something that was recognized when